Example 19. The gas in the cylinder of a diesel engine. Okay, this diesel engine is probably inside a car. Now in a car, there's a car engine. In a car engine, there's actually a gas inside the cylinder, and the gas is actually continuously being compressed and expanded. And so if you look at the gas at, let's say, at state A at the beginning, this is the initial pressure and this is the initial volume. It is compressed to a very high pressure and it's allowed to expand, and then in the last stage it's allowed to cool off, giving off some heat and cool off back to the original state, and then it undergoes changes again, the repeated same cycle. So it undergoes cycle after cycle, but during each cycle the gas is actually doing some work, and the work done by the gas is used to drive the car forward. Okay, so that's what happened inside the car engine. The gas is undergoing all these changes, but in the process it actually does some work to drive the car forward. Okay, in this question we are given a table that give information on each part of the cycle, A to B, B to C, C to D, and D to A, and some values are given. And part A, they ask us to calculate the work done on the gas during B to C and during D to A. Now earlier on we know that there's a formula to calculate the work done, but that formula can only be used if the pressure is constant. So let's check it out. For B to C, is the pressure constant? Yes. From B to C, the pressure is constant. So that means the work done during B to C, we can use the formula to calculate the work done. Okay, the formula for work done, the work done by the gas is equals to P delta V. Okay, work done on the gas is sort of like opposite in sign to work done by the gas. If the work done by the gas is P delta V, work done on the gas will be just negative P delta V. Okay, so we're going to sub in. Okay, this is the pressure, then times the change in volume, final volume minus initial volume. Okay, that will work out to be equals to negative 736 joules. Okay, the work done on the gas during B to C got to be negative because it is expansion. Okay, in an expansion, the work done on the gas is negative. Only when the gas contracts, then the work done on the gas will be positive. Okay, then next find the work done during D to A. Okay, let's check out what happened during D to A. If you look at D to A, the volume remained constant. That means there's no change in volume. What is the work done when there's no change in volume? Well, the answer is 0. Okay, when there's no change in volume, there will be no work done. Only when there's a change in volume, then there's a work done. If the volume increases, expansion, work done on the gas is negative. If the volume decreases, contraction, then the work done is positive. If there's no change in volume, there's no work done. So now we can fill up the boxes here for the work done. Okay, so during B to C, the work done on the gas is negative 736 joules. And the work done from D to A is the work done is 0. Now, once we fill up the first two columns, Q and W, we actually can figure out the third column, because according to the first law of thermodynamics, delta U is actually equals to Q plus W. So for process A to B, the delta U will be equal to 0 plus 300. So the answer here will be 300. And likewise for process B to C, the delta U will be equal to 2576 plus a negative 736, and that will give you 1840. And likewise for process D to A, the delta U will be minus 1700 plus 0, and that will give you minus 1700 joules. And then once we fill up the three part of the cycle, we actually can figure out what is this part here, Because we know that in a cycle, the total change in internal energy will be 0. This is because in a cycle, okay, let's say start from A. After one cycle, the gas returns to its original state. If it returns to its original state, it will return to its original internal energy because everything is exactly the same as before. Same pressure, same volume, same temperature. So in one cycle, the gas returns to its original internal energy. The overall total change in internal energy in a cycle will be 0. So that means 300 plus 1840 plus watts plus negative 1700, they all must add up to give you 0. So that's how you work out this value. Okay, so that is part C. Okay, by the way, that's the part B answer. We're using the first law of thermodynamics, A to B, B to C, D to A. Okay, we can work out the delta U for each part of the cycle. Then for the process from C to D, we make use of the fact that all the individual delta U add up in a cycle will add up to give you total 0. So from here we can deduce that this box here will be negative 440 joules. Okay, so we can fill up this third box here. Okay, negative 440 joules. And once we fill up this box, we can deduce this box because, again, according to the first law of thermodynamics, Q plus W will give you this number. So this value because this value plus this value will give you negative 440. So if this is negative 440, we can deduce that this is negative 440. Okay, so that completes the table.